Welcome back to the second session of the XPAG workshop HPC Asia 2021. So in this second half, we have one invited talk and two full paper and one short paper presentations. So at first, I'd like to introduce the Joe Curley from Intel for his invited talk about the oneAPI. So Joe is an long-term working very special engineers in the Intel, and I personally have a very good contact with him when after we introduced our first KNL cluster. So thank you very much for that time. So anyway, today's Joe's talk is on the oneAPI. Is one of the very hot topic from Intel today for their accelerated computing and programming and working framework. So Joe, please go ahead to share your screen. Okay, please go ahead. Joe, your mic is
yeah. Yep. Thanks very much. I just had to display and turn the mic off. Can you hear me now?
Yes, clearly.
Very good. Thank you. Thank you so much, Boku Sensei, and thank you so many good friends and partners over the years for joining us again today. Many familiar names on the phone, and it's a pleasure to be with you again. I also must say it's a pleasure seeing the Oak Forest PAX machine in the background. It brings back many good memories of the last time I was able to speak at HPC Asia and at XPAG. My name's Joe Curley, and for most of the last 10 years, I've worked in the high-performance computing business in a number of different roles, either in strategy and planning, or in working with the ecosystem on trying to build out high-performance applications, efficient threading, vectorization, and this is where many of our last conversations came from. In June, I joined our internal software organizations to drive a new initiative, one that we call oneAPI. And if you have not heard about it, in the next 25 minutes, what I'd like to do is give you an idea of the problem that we have seen and customers have come to us with, our approach to the problem and the solution space, and then perhaps suggest opportunities that we may be able to collaborate together in the future, as we have collaborated so well in the past. The first problem I wanted to start with is just talking a little bit about acceleration technologies. And it's important when you think of accelerators, not simply to think of attached accelerators. Of course, FPGAs, GPUs, deep learning ASICs are quite common, especially in specialized systems today, and for high performance computing to get energy efficiency and to achieve extreme scale. It's only half of the problem. In fact, many new diverse acceleration technologies will be built inside microprocessors going forward and through lots of different methods of integration. Many new technologies will be taught, you'll hear about over the next couple of years to make this easier, but there will still be complications. Some of the changes will happen in interconnect through things like compute express link and having coherency between accelerators in shared memory space, shared caches between the host and the accelerators. The programming model can simplify for the developer. But other devices will remain in I/O space. Some devices will appear to be part of the microprocessor through on-package high-speed interconnects. In fact, our upcoming GPU, codenamed Ponte Vecchio, will end up actually having a combination of both interconnect on a single package as well as stacked interconnects. We call these technologies EMIB and Foveros. Inside our microprocessors, things like advanced matrix acceleration will start to show up. This extends some of the ideas that we worked on so hard together over the last 10 years, just enabling AVX, AVX2, AVX512, and efficient threading. Beyond that, there's diverse cryptography accelerators, data movers, DMA engines. All of this to create performance for the specialized workloads that are coming into the marketplace today. But it creates a problem. Given that growth in specialized workload, there really is no one microarchitecture that's ideal for all. GPUs are quite excellent. Data parallel, dense linear algebra, a number of other functions that they've been quite useful for over the last decade. We have microprocessors that handle the scalar workloads for things like streaming packet inspection, streaming data types. FPGAs and spatial accelerators have unique attributes. And as we look at deep learning, matrix processing becomes much more consumable. So you have sometimes inside packages combinations of these. A GPU may have a vector engine and a matrix engine, or they may be separated inside the system. And I think over the long haul, we'll start to see things distribute in very new and interesting ways. And this is good, because if you can't predict what workloads you will have, having this diversity of accelerators to be able to run them should provide for greater energy efficiency, better science. But of course, there's a problem that comes from this, and that with each one of these individual accelerators, you have to learn to program them. And we've talked about the subtleties of adding things like frameworks, deep learning frameworks, where you can abstract the underlying hardware. But even so, there are differences from device to device. We just had a wonderful talk on trying to figure out how to be able to get lower precision math enabled inside a standard microprocessor. How do you move that to a GPU or an FPGA? And worse, as most of these accelerators are actually being used, many have very specific and dedicated programming models. CUDA, ROCm, OpenCL. It may end up having, for our FPGAs, the wonderful Quantus tool sets. All of these different devices, you have a separate set of tools, a separate set of languages that you have to train, deploy, you have to maintain code bases for, you have to update, change, refactor as necessary. So all of these things create a very simple problem. If you just start with only simplifying things to 4 individual microarchitectures, and you multiply that by anywhere from 3 to 5, 6, 7 vendors, you add a tool chain per implementation, and what you get is a problem. And the problem ends up being either underperforming hardware, inability to use the hardware, limited numbers of applications using your acceleration technology, or very commonly you'll just say, I may have a better choice, but I'm not going to use that because my code was already written for another accelerator and I'll just stay there. That's the problem statement. And to try to work on that, Intel has gotten together actually with members of the industry. I'll talk about some of them at the end. Some members of the Intel Extreme Performance User Group and other even competitors in the space to try to define a new standard, which we call oneAPI, and it's an industry initiative, and it's intended to solve the fundamental problem of dealing with how you can try to find a way to scale and effectively program diverse accelerators with diverse microarchitectures in a common tool chain. This should enable a couple of different things. One, you should get greater code reuse across different accelerators from different vendors, and hopefully free you up from some of both economic as well as technical challenges that come from reliance on one single proprietary toolchain. In order to do this, the specification handles 2 different major elements. One is a common data parallel language, an abstraction language that allows you to program accelerators. And this language is codenamed Data Parallel C++. We'll talk a little bit more about it on the next slide. The second thing that we try to define are standard library interfaces that can be used to have a common call into a library interface and then call through optimized libraries for each of the underlying accelerators. So for example, if you wanted to work with an Intel GPU in the future, you would be able to call oneMKL, which would then have an Intel math library or math oneMKL library, and then our underlying hardware. But it doesn't have to be Intel. There are other instances that people have looked at, for example, using oneDNN into other microprocessor architectures like ARM, or even we've seen proof of concepts with cuBLAS underlying it for NVIDIA GPUs. So a standard set of library interfaces to enable productive scaling of accelerator applications. And that's the initiative that we're trying to build. And this is normal. When you have an industry in its innovative phase, many different experiments, many different proprietary instances exist, but at some point, the industry coalesces and comes together to come up with a scalable, economic, and viable solution. And that's what we're trying to do with the oneAPI initiative. Data Parallel C++ is the language that we use inside this initiative. And Data Parallel C++ is a combination of 3 different elements coming together. First, we start with ISO C++. But on top of that, for addressing accelerators, we've worked with an open standard language, Kronos SYCL. And SYCL has a number of very definite advantages as a programming language. One, it's very C++-like. It integrates beautifully into C++, combines the host and accelerator codes into a single page. So it's more productive, it's easily recognizable, and it's readable all inside one screen. Secondly, it's an open industry language. And by that, it's run by Kronos. It takes recommendations from the industry. It's not owned by any one vendor. It has the ability to innovate across vendors. And it has a growing multi-vendor ecosystem. In the backup links for the presentation, which you can download from the XPUG website after this speech, I have many links to talks on Kronos SYCL, which you can listen to and look at the implementations that are being built for other microarchitectures, including NVIDIA, our own microarchitecture, AMD, and others. So we combine the idea of an open language and an ecosystem. And then the last thing we put together is community extensions. And Kronos SYCL has a number of great features, but it had a number of gaps for being productive as a broad accelerator language. So the community suggested extensions. We tested them out through our period of beta and did 2 things with them. One, we rejected ones that didn't make any sense. And the ones that did, we were able to actually propose, in many cases, right back to Kronos to be integrated into the proposed Kronos, the latest Kronos specification. And so eventually this too becomes standard, usable, and scalable. So a common data parallel language. And then the second thing we do is we build out standard interfaces to commonly used libraries, math libraries, the deep neural network libraries, video processing, data analytics, threading, collective communications. We looked at the Horovod example earlier, how we are able to try to get scaling inside AI systems. And then a parallel standard template library for the data parallel C++ language. All of these are specified in the 1.0 version of the oneAPI specification. And I was really thrilled to see recently a blog from Fujitsu, who has actually already taken the beta oneDNN specification back in November, made it available, ported it to A64FX on the Fugaku system, and has made it available to their users, and really proving the concept of openness and the idea of being able to have a common CPU interface that is used for an Intel CPU, but also can be calling the optimized ARM libraries underneath it. So scalable, standardized library interfaces that give you some freedom of choice, but also productivity and greater reuse of the code that you've invested in for your machines. So with that, we have a specification, and that specification is useful but we wanted to, a spec is useless without a proof of the concept. And so Intel has moved forward in only 1 year from the announcement of this initiative to actually shipping in production our first generation of a product built on the oneAPI specification. Intel's oneAPI product comes with 4 major elements. And we already talked about the languages like data parallel C++, but there's quite a bit more that I'll describe on the next slide. Additionally, implementations of all of the libraries we described, oneMKL, oneDNN, oneCCL, are included in our first generation product. But they also come with the analysis and debugging tools that you would expect for not only a CPU, but extended to what we call XPUs. And XPUs are accelerated processing units, wherever that acceleration may exist, in the CPU, attached physically, attached through a coherent bus, or attached in I/O space. All of these XPU architectures can be supported through the model that we have with Intel's oneAPI product. And the last thing that we include is a novel, and I'll talk a little bit about the feedback we're getting from our developers, and you can see some videos on this, is something called the Data Parallel C++ compatibility tool. And what that allows developers who've worked in the popular CUDA language to migrate their code from CUDA to Data Parallel C++, or from a closed proprietary language into an open and a scalable language for the future. The objective of the compatibility tool is to translate or to migrate about 80% of the code. With any accelerator language, there are some things that are very tightly coupled to the microarchitecture. If that happens, then the tool will also give you hints of how you can program that in an open language and get up and running. And again, in the links, we'll be able to give you some links to people who, through the beta, experimented with the tool in its very early phases when it sort of worked, and as it improved all the way into the production that we shipped in December. So all of this eases transition for developers from what they're programming today, either from the current C++ world through a very readable and productive language in Data Parallel C++, through libraries that you know and understand, or through migration from a language that you may have been writing in into Data Parallel C++. Today, we have a vision of being able to cover all of Intel's XPUs with our product. We're not quite there yet. So what you have today in the element, what you have in the specification are a number of things. And starting from the bottom, oneAPI defines a hardware abstraction layer called level 0, which can be implemented for diverse hardware. And this helps for people lying higher in the stack, for library developers. It creates a virtualized interface that helps them write more effectively and get greater scale out of the libraries to diverse hardware underneath. Today, we have it available on Intel GPUs. In the future, we'll look to expand it to other Intel devices. For our FPGAs, which you can program through oneDPL and Data Parallel C++, we also have an OpenCL runtime today, which is capable of compiling and running the Data Parallel C++ and then executing it through an OpenCL runtime. Over time, we'll fan this out and make it available through level 0 as well. I'll talk to you a little bit about the concept of toolkits, but in our distributions, things that are not, we also include some things that are not part of the open industry specification yet. Python and Numba. Our standard Intel C and C++ compilers with oneMP. We have a part of the oneMP 5.0 and 5.1 spec implemented today. Over the course of the year, we will continue that, and by the end of the year, we'll have the complete specification ready to intercept our own GPU, getting ready in advance of our own GPU discrete offerings and with our own integrated offerings. And then, as you start moving up the stack, we have all our threaded building blocks, data analytics library, collective communications library, neural networking libraries, and math kernel libraries already enabled both for CPU and GPU. So things, if you've used the Intel tool chains in the past, these should all be familiar to you. And now we've taken things that have been very common and standard for the CPU and extended it into the XPU world. It's probably worth noting also, if you haven't worked in the past with Intel tools, because they've been a commercial product, another change that we have is that the tools today are, all of these toolkits that I'm speaking of, available for you today online, free of charge for download. And we'll talk a little bit about the mechanisms to do so. But we start with an idea of being able to make one product available for all kinds of developers. For general purpose developers, we have a oneAPI based toolkit. It includes the language, basic libraries that are commonly used, basic tools that are used by most developers. But for size, maintenance, familiarity, we only include base elements that general purpose programmers will want. For high performance computing, we have specialized toolkits that you can add on to the oneAPI specification. So, for example, the Intel MPI, Fortran compilers, both our classic Fortran compiler, as well as a new LLVM-based Fortran compiler with offload for GPU, are all bundled together with other specialized tools and analyzers into the HPC toolkit, again, available today through software.intel.com. Although this is a first generation product, we went through a series of 10 betas over the course of the last year. And in November, we hosted the first oneAPI Developer Summit virtually online. We normally would like to have done this before supercomputing. In that, 19 different developers came and gave their very candid, unfiltered input on how things were working and what they were able to do. One such case study came from the SUSE Institute in Berlin, working on a tsunami code that they call EasyWave, which was written in CUDA as part of their own scientific suite. They tested out they wanted to test out the tool chain, and the promise of portability is interesting, but did it actually work? And for this code, what they were able to do was, using the compatibility tool, migrate from CUDA into data parallel C++, and then start to be able to run it on the CPU on Intel's integrated GPU on our Stratix FPGAs. And interestingly, they also picked up a compiler from a company called CodePlay, which has a SYCL and data parallel C++ compiler, and ran it on an NVIDIA GPU. And what's interesting is that the results of the data parallel C++ code generated were within 5% of their CUDA code that they started with. Now, that's quite an exceptional result. I don't know that it will happen every time, but their experience was really good. They talk about this on the online recording of their talk. They mentioned they ran into a couple of problems with the FPGA, how they worked around that, how they dealt with microarchitectural differences between the more vector-oriented CPU and GPU and the more spatial FPGA, but the performance results they were able to get from that as well. And this was a wonderful testimony to learning, a number of interactions we had through the beta, great community feedback of what was working, but also that the promise exists to be able to use a single code base across all of these diverse accelerators. And as I mentioned, the workflow was to start written in CUDA and then go through a compatibility tool into the DPC++ language. Also online, through the links, if you want, we can talk, the first was what worked. Eric Lindahl, who is the key developer for the GROMACS application, keynoted the second day of the conference and talked a great deal. I'm talking about the promise and what we're trying to do and what our initiative's about. Eric treated it much more practically. He said, I'm a developer, I love your vision, but I need something that works. And he gave a very, very honest assessment of where we were in the beta as of November of last year. What worked, what didn't work, what things you would write for the GPU, what you would reserve for the CPU, how to think through the problem for a massive code like GROMACS. But one of the most interesting comments that he made was that the specification was open, that he sits on the technical advisory board for the language and takes inputs from the community and drives them, which is some of the ways that people have been able to get oneAPI working experimentally on ARM microprocessors, or being able to work in other environments. Open, he concluded, is actually open. And that was one of the most, that was unprompted, and he's very honest about how little interaction we had in his content. It was one of the things that we were most rewarded to hear, was that we were responsive and that we were open to the community and helped create an environment that could be both productive and cross-platform. And Eric, will, if you want, I strongly encourage you to listen to his talk. There's not any marketing in it. So we've talked a little about the vision and a little about what we include inside the initiative, why we're trying to do it, how we're implementing our first product. If any of this is interesting, we have multiple ways for you to be able to test this out for yourself. And one of them is you can quickly just go to the Intel website, software.intel.com, oneAPI, and go grab the tools. And they're available for free download. You can start working with them. Please give us feedback. This is a Rev 1.0 product. We are at the beginning of a long journey. We're hardly complete. And users actually using the tools are required to make this work as wonderfully as we expect to. If you don't have an Intel system handy and you want to try them, we actually have an open thing called the Intel Dev Cloud. Links also exist here. You can go through and sign up, get an account, and be online. I was online with my account in a matter of minutes, and up and running test codes almost immediately. And we provide diverse hardware up there for you to experiment with. Our own Xeon processors are integrated and now discrete first-generation graphics cards. Our Area FPGAs and our Stratix FPGAs are all available in the Dev Cloud for development, experimentation, and feedback. And again, all of this is open. It's free for not only the members of the Xpug community, but all comers. So with that, I'd conclude by saying that we see a future of diverse, heterogeneous, accelerated computing coming. The challenges that will create for science is figuring out how to get the most out of the hardware in the least time, and to do so in a fundamentally scalable, open, and economically viable fashion. To help solve that problem, we've proposed oneAPI and have completed the first oneAPI 1.0 specification. If you are not an Intel customer, or if you're developing your own hardware or your own accelerators, we encourage you to go to oneapi.com and read the specifications. Consider adopting it. The benefit you'll give your users are common interfaces to be able to move code around the industry much more quickly and much more effectively. If you are using Intel hardware, try out our implementation. I might have mentioned that it's free, and that you can get it for your own systems and use it today on Linux and on Windows. A subset of our tools are even available on the Mac. Additionally, you can try it inside our Intel Dev Cloud if you don't have access to an FPGA and you wish to see the FPGA, for example. So I'll simply conclude by saying that the approach that we've taken, at first people wondered, were we serious? Would we ever get the product shipping? And as we've gone through our betas, more and more have joined in the initiative. We're pleased to see competitors picking it up. We're seeing polls for some of our toolkits from other microprocessor and accelerator developers. we've seen some announcements from people already deploying our library, some of our libraries like oneDNN. We'd encourage you to join. And with that, I would like to thank you very much to the leadership for the XPUG group, Professor Boku Sensei, and all of our friends for giving me the opportunity to talk to you today and hopefully interest you in joining the initiative.
Thank you. So thank you, Joe, for the great talk. And now we have about 5 minutes of the QA time. So if you have a question, please write chat, or maybe you can just turn on your microphone directly ask a question or a comment. Is there any question or comment? Okay, so in case I have one, so Joe, could you show me that the slide of the tsunami simulation on the oneAPI, maybe the first example? Yes, and one page before. Yeah, so I'm curious that you or they applied their application onto the multiple devices individually. For that, I'm very curious that performance of the Stratix 10.
Oh, I should have that on the top of my head. If you'll accept my humble apology for that one data point. It was initially quite poor, and I think underlying your question is, to what degree is if you move from a vector architecture to a spatial architecture, do you see transparent performance? They quoted what their results were actually in their talk online, and I cannot remember it right now. But the thing I will comment on is, you make an excellent, the question you ask raises an excellent point. No language, the beauty of accelerator languages is that you can write and optimize for a given architecture. Of course, the moment you do that, you are optimal on one and suboptimal on the others. So you can be portable across multiple architectures, but performance portability will always be a challenge. The thing that we promise is the ability to generate code and run it on multiple devices. So at least you only learn one language. And we give you the tools to be able to optimize for many. And in the case of dramatic differences, there may be some strong code changes or if-defs that you would end up doing for the differences between spatial and vector, for example. Mm-hmm. But you don't have to teach a new. You don't have to teach a new language. You don't have to teach you don't have to deploy a proprietary tool chain. You don't have to have multiple code bases and stacks that you're working with under this circumstance. So the performance portability is always going to be a question. There's no magic, but the rest of the problems do get solved.
Okay. Okay. Thank you very much. Is there any other question? Okay, in case there is no more questions, so I'd like to conclude this invited talk session. Thank you very much, Joe.
Thank you so much for having me.
Okay.